Hello guys, welcome back. And in this session, I'm gonna talk about the physical memory protection feature in RISC-V. So this is the content for this session, and it might be slightly longer than the normal video. So what I'm gonna cover in this session is that the physical memory protection, or in short, which is a PMP feature. And this is part of the privileged spec in RISC-V, which talks about the maximum number of regions a RISC-V core can support, and what are all the permissions that each region can be provided, and those associated CSR, or the control and status registers, and their layout, followed by PMP implementation in E31 core, and this is the core which is there in Hi-Fi 1 revision V board. And we will also see a sample PMP configuration for a given memory. This is for a hypothetical memory map, or for a given memory map. And finally, as usual, we'll do some sample code run on Hi-Fi 1 revision V board. And in this, I would create regions with different permissions, and we'll see if PMP works or not. Okay. So if you wonder where to get the PMP in the privilege spec, all you need to, so this is a RISC-V privilege spec, and version 2021 is what I have. You can just search for PMP, and you would hit this page of section 371. Okay. So this slide captures majority of the PMP section, which is covered in the privilege spec. Okay. So as per the spec, the physical memory block can be split into a maximum of 64 regions. That means that as per the RISC-V spec, a RISC-V core can have maximum of 64 regions, and each region can be configured with a set of permissions. Okay, and so the configuration corresponding to each region is about 8 bits or a byte. Okay, and most importantly, that this is a physical memory protection. That means that physically addressable memory can be protected using PMP, whereas if you have a MMU, and if the processor supports virtual memory, then PMP does not protect those virtual memories. And I also would like to mention that this PMP feature, as per the spec, is an optional feature on a RISC-V core. It's not a mandatory one. And the spec also mentions that the minimum size for a region can be 4 bytes. And as I mentioned, there can be maximum of 64 regions or entries. Okay. And these purple colored ones are all CSRs, and it's part of the spec, and every RISC-V core should be compliant to that. So each region has a PMP address CSR associated with it, and also has a pmpaddrX config field associated with it. Okay, we will see more on this soon. So this is the CSR layout for RV32. So each region would have a PMP ADDRX, so X can run from 0 to 63, has an address register which holds the region's address. But if you see on a 32, so the address here should be from 2 to 33. That means that the base address should be right shifted by 2. And for the configuration or the permission for each region, as I mentioned, that it would correspond to 8 bits if you see here. So it can be read, write, execute, and there is an A which stands for address matching, and 2 bits are filled with zeros, and the MSB or the 8th bit is for lock. Okay, so each region can be configured with 8 bits permission, or we call that as a config field for the region. So the configuration of 4 regions are coupled into one PMP config register. If you pay attention, you would see the number between the PMP and CFG in the field, whereas you see the index at the end of the PMP CFG CSR register. So this purple one are a CSR register which are 32 bits wide, whereas these fields inside for this is 8-bit field in a configuration register. Okay, so on E31 core, so as you know that the RISC-V spec is the guideline, and any manufacturer who generates or who manufactures or who makes a RISC-V course, they can always just have to stick to the guideline and create a subset of it. For example, in E31 core, there are only 8 regions, so it just supports a maximum of 8 regions. That means that the physically addressable memory can be only split into 8 regions, and each region can be configured with a set of permissions. Since there are only 8 regions and each region has a byte to configure, just 2 PMP config CFGX registers are enough to configure those 8 regions. Okay, and coming back to this permission or what do you say, configuration field for each region. So these are all the fields, as I mentioned before. You can give permission for the region to be just read, or read, write, and execute, and this A is what you would see here, and L stands for lock. Okay, so this address matching field, it will be more clear once we at the end of the session, but for now all you need to remember is if it is 00, that means that PMP protection is disabled for that particular region, in which case the particular region would be accessible to machine, user, and the supervisor mode. And if the 8-bit fields are 01, which stands for top of range, and 10, which is naturally aligned 4, and 11, which is naturally aligned power of 2. Okay, let's look into the sample PMP configuration for a given memory map, and this is what is exactly given as an example in E31 manual, but this memory map does not correspond to the E31 core. This is just an sample memory map which E31 manual has taken a sample and tried to configure, and to help the reader to understand better. Okay, so for example, let's go through each region and how it's configured in this sample. So first, 64 kilobytes is flash memory, and read and execute permission, to give read and execute permission. So the PMP, so this is a first region, so the address register 0 is used, and if you take this top address for the first range, which is 0x001 followed by 4 zeros, And as I mentioned before, this is right shifted by 2 and it's written here. Okay, so we will see in the next slide how this value for ADDR is arrived, but on the config field for this region, on providing the permissions, it's straightforward. So 8 bits for this. So this has read, write is disabled, and execute permission is given, and 0, 1. So if you see here, 0, 1 is top of the range. And what does the top of the range mean is the register or the address which is given in the PMP ADDR register is the top address, not the start address. Whereas if you go to the naturally aligned power of 2 configuration, the address whatever is there in the PMP ADDR would represent the start address or the base address of that region. Okay, so to give no access, if you see here, okay, this is wrong. I think I just copied from here to here. Okay, and I see that read write. So read write, you can see the bit fields here. The write, so read write permission is given, but whereas for no access it should be 0, 0. And this is a naturally aligned power of 2, except the first one which is top of range. Rest are all naturally aligned power of 2. Okay, so if you wonder, there is one register for address and there is another register to give the permissions, but there is no register to mention the size of the region size. So that's why this is so good, that it reduces the register count by 1 by encoding the size of the region in the address register itself. So from the base address, so what this table, so this is from the spec and this is from the FE31 or E31 manual. So both gives the same information but in a different way, except that in the E31 manual it is so easy to understand, but both are the same. We'll see how it is. Okay, so what this manual says is, if you have a base address and if you want to configure the size of the region from the base address to just 8 bytes, which means that, let's say that you want to create a region starting from, say, 0x2 followed by 7 zeros until the next 32 bytes. If you want to configure that, then what you do is you take the base address and right shift by 2, that means this is the 33 to 2, and or with 3, that means the last 2 bits should be 1. Okay, and how do you get the region size is, so either you can use this table, and sometimes, for example, if you want to create the next entries on this table, what all you have to do is, so the region size would be 2 to the power least significant 0 bit plus 3. So for example, you take this one. So the address is bitwise odd with the 0, 1, 1, and if you see the least significant bit 0 position, it is 2 here. So 0, 1, 2. So 2 plus 3 is 5. So 2 to the power 5 is 32 bytes. So let's apply this formula and see if this works. So let's take this row 3, and if you want to configure a region with size 4 kilobytes, then you take the address and right shift by 2 and or with this bits, and you have the LSE, or the least significant bit here is at a 9th position, and or the least significant 0 bit is on 9, so 9 plus 3 is 12, so 2 to the power 12 is 4 kilobytes. So either you can use this bits directly, or you can just use this formula to generate the region and configure the PMP ADDRX value. Okay, and it is the same. It's how it's mentioned in the spec. So except that instead of exclusively mentioning that this register values should be odd with this many bits, it just says as if it's filled with ones. Okay, so otherwise it's the same, and I find it easier. I find this table, which is given in the E31 manual, easier to understand. Okay, now let's demystify one of the configuration. We'll take one region. So what I have done there is I have taken this particular region, okay, and we know that this is the value for this, and let's see how this value is arrived. Okay, so first for this region, this is a lower address, and this is the a top address. So 32 kilobytes is the region size. So to encode the PMP ADDR, all we need to do is take the base address, right shift by 2, and you would get this. And for 32 kilobytes, since this is, you want this region to be 32 kilobytes, you are with 32 kilobytes, you are with these bits, and this is what you would exactly get. And you fill the, or you write PMP ADDR register with this value. Okay, and for the permissions, or the permission settings for this region, this is read bit, a write bit, and execution is prevented, X is 0, and then address matching is 1 1, which is naturally aligned to power of 2, and then a hardwired 0 bits, and the lock is enabled. Okay, so this is another example for top of the region configuration, and you can see here there are, I have taken 2 examples. The reason is, if the top of the region is the first region, or if PMP ADDR 0 or the first region is configured as top of the region, then the address whatever is given would be considered as a top address, and the lowest address would be considered as 0. So this address matching would apply to any address between 0 and to the address that is mentioned in the region, if the 0th region or the very first region is configured as TOR. However, if a region other than the first region, let's say this is a second region which is configured as TOR, then the address matching would be applied to the address whatever that is mentioned in this region, and up to the lower address of the address which is there in the previous region. For example, if this region is configured as TOR here, then the address matching would be done between the address in the previous PMP ADDR register and the current one. That's our only difference. And the address matching bits would be 0 1 instead of 1 1 as in NAPOT, or naturally aligned power of 2. Okay, now let's get into the most interesting part, which is the coding. So I have created a new directory, inside the apps, and call that as a PMP. And this is the main pmpaddrX file, which has all the PMP code. And I have also committed this into the GitHub dev repo. If you go to the development repo and if you go to the apps directory, and this is the code which I'm talking now. Either you can, if you want to access the code, feel free to use it from the access it from this Git repo. Okay. And I like to use Visual Studio's code so that these fonts are bigger and easy to read. Okay, so as usual, and as most of the time, I'll just I mentioned that. So right after the reset, the execution will jump into start entry, and I just set the trap vector base, and then jump into the app entry, and that app entry would be the one of the every app directory here would have the app entry, and it would jump into this label here in this pmpaddrX. Okay, and here, so when the execution jumps into this app entry here, it would still be in the machine mode, and here I modify the machine previous mode, MPP, to user mode, and then once this mret is executed, whatever the address there in the MUPC, which I have set it as the user mode entry address, which is this, the execution would jump here, but by this time it would be in the user mode. Okay, so in this PMP demo app, I have created two memory regions. Okay, one is the top of the range with the config top of the range, and other one is naturally aligned power of 2. Now I'll show you why I have chosen this address for top of the range. First, let's build. So if you see, this application has, since I load it on RAM, it starts from 8 followed by 7 zeros. That is the start address. That should be the start address. Okay, and all the way up to 5E8 is the code in the RAM. So I do not want to disturb, so I have given some extra buffer and configured the top of the range address as this, so that I need, if I want to give permission for this range, that should not be any problem for the code to execute. Okay, so first let's see what happens when all these are commented. I have already discussed this in the previous video on machine to user mode switch, but anyway, I would just want to start with that so that we know what would happen if the PMP is not configured. And okay, so let's build again. So I'm just stepping into until, oops, sorry. I need to reboot the board. Give me a minute. So from the start entry, now the execution has jumped into the app entry here. So let me step in until, so we are it's now setting the status. Okay, let's it's writing into the MEPC register. The user mode entry address is written here. Now, since I have commented all this, next instruction is a mret. But right after that, if you see, the execution has jumped into the trap base because some exception has occurred. If you want to see what that is, mcos, it says 1. And if you go to the manual, and this is interrupt, exception 1 is instruction access fault. And if you read, so this fault is, so whatever this exceptions you are seeing in the E31 also converges to the same in the privilege spec, so you can refer any of this. So the, if you see here, the as per the spec and as per the manual, if the permission is not enabled and when it is tried to access the instruction, that would result in instruction access fault. Okay, so now let's go ahead and enable the user mode execution permission for this first region. That's why I set this first region up to this address. This means if this region is set as region 0 as top of the range, that means any address from 0 to this would be set with this permission. Okay, so the permission which has been set for the 0 region is 0 FFF. That means that let's go to this. So 0 FFF would be like top of the range. Okay, so that's good. And since it's a 0th region, or the very first region, that would correspond to the LSB byte of the PMP CFG0 register. Now let's build again. Oh no! First, I should reset the board because the trap has already occurred and those bits will be set. So I just want to reset the board. Now the execution has come to the app entry and it should configure this PMP registers. Let's see, status MEPC and the right shift by 2, and it's writing into the register value. So if you see instruction register 0, so this value is right shifted by 2, and that's the top of the range. That's it. Now config PMP-CFG0. So read, write, execute, and it said address matching bits are 0, 1, which is top of the range. So no problem when the execution jumps from machine to user mode. That should not be any problem. See, now execution has jumped into the entire user mode code, and you can see here without any problem it's executing all this functions, or sorry, all these instructions. Okay, so next I have created another region with the base address of this, but config I haven't set it, okay, because this is commented. So here if I try to read the value, let's see what happens. So now it's added this value, and the result should be in T0, right? T0. So I'm trying to fetch a word from this address, and this address falls in this range. See, now again the execution jumped into the trap handler, and if you see this time the exception is 5, and let's see what is 5. 05 is load access fault. That is because so failed read and write permission. So if the access is denied, then since I'm loading here, it should generate load access fault, because in user mode is not granted permission to read from this NAPOT region. Okay, so what I'm going to do is I would just uncomment this line, and for TOR or top of the range, you don't have to mention the size, but whereas when you configure a region as natural element power of 2, you have to set the size. And if you remember this table, for 32 bytes, you have to just OR with the number 311. So that's what is exactly I do here. So starter is this, and I set the size as OR with 3, which means 32 bytes. So from this up to 32 bytes has been first set to the permission like 1 and 9. So 1. Sorry. What's that? So 1 and 9 would be read permission and no write, no execute, and 1 which is for NAPOT or natural element power of 2. Okay, now this has read permission alone. So let's see if the load goes through. Okay, so now I have to reboot the card. Let's see. So let's build. Okay, right now it's in the app entry. Let's state as MEPC, and it's configuring address ADDR0 and ADDR1. Now finally CFG0. Okay, so now CFG0. Okay, for the region 1, it's the value is set 19, which is good. So now let's return from this, and now the execution is in the user mode. So now this address is loaded into the T0 register, and it's gonna load or read from this particular memory address. Let's see. Okay, so load has been successful, but that means the read is successful, but when you try to store, the exception has occurred. And if you see the MCOS, it's 7. That is the exception. And let's see what that exception is. 7 is store access fault. Okay. So this is how you can configure and grant or deny permission to user and supervisor level privileges. And in E31 -1 revision B board, the E31 has supports only the user mode. Okay, so that's the so we are done with the coding, and now if you are interested, you can read or trying to find. If anyone is interested in knowing more or learning deep, then you can see if how to configure memory regions, or how the memory regions would work for idempotent versus non-idempotent memory. So what I mean here is the memory where for example, if there is a memory mapped peripheral IO registers, then fetching, because those registers values can be volatile. So how this PMP would work on those, and also, is the PMP configuration allowed a runtime? Is it allowed to configure this when, for example, let's say that in the machine mode, it's first a particular region is granted permission to user, and after some time, if it wants to revoke, can you do that or not? And is overlap, memory region overlap is allowed or not? And is a configuration, is the PMP configuration allowed only after the reset, or it can be done any number of times during the or even after boot up? Can it be changed? These are all the things that you can dig, and if you're interested, you can go ahead and read further. Okay, and thank you. And if you're interested in more videos like this, and don't forget to click the like button and subscribe button. Thank you.